Donna, and she is going to be talking about the energetic particles at our evolving Earth. So take it away, Donna. I'll give you a 3-minute warning.
Cool, great. Thanks, Megan. And thanks for giving me the opportunity to present my research, which is I'm currently at Trinity College Dublin, and I work mainly with Eleni Vidoto. So today I'm going to be talking about energetic particles and how that's interesting to people who are interested in magnetic fields. So one of the main questions that I'm interested in is relating to the habitability of exoplanets. So if an exoplanet is in the habitable zone, as Joe was mentioning earlier, just because it has liquid water on its surface doesn't necessarily mean it's habitable. And I'm interested in this question from the point of view of the impact of energetic particles. And so I'm going to talk today about the sun and the earth in the past and the conditions that would have been present in the early solar system. And then Amanda Mesquita is actually going to talk about the impact of energetic particles on dwarfs later this in a few more talks. So the main question I'm going to focus on for my talk is, when in the sun's past were stellar energetic particles more important than galactic cosmic rays? And these are the two types of energetic particles that I'm going to talk about for my talk. And I'll explain why they're important for exoplanet habitability. So first of all, just a kind of a refresher to change from stellar wind modeling to energetic particles. What are galactic cosmic rays? So they're relativistic particles, mainly protons, which we detect at Earth. And so here on this sketch, you can see the galactic cosmic rays basically sit outside the solar system. It is a sea of them, which we detect, and they penetrate through the astrosphere of the solar wind, and then they reach Earth. And then at Earth, there are stellar cosmic rays, where stellar energetic particles are accelerated. And so here, zooming in, this sort of shows you a zoom in from around the sun. So solar energetic particles or stellar energetic particles for other stars are accelerated in flares or CMEs, which then propagate out and impact on exoplanets or Earth in the case of the solar system. And solar energetic particles are the same as galactic cosmic rays in the sense that they're still relativistic charged particles, so they interact with magnetic fields, and they're just usually lower energy because the sun's not such a great accelerator. And for the sun, these solar energetic particles come in bursts, so we don't see them all the time, whereas the galactic cosmic rays are pretty much the same, except for actually the fact that they are the number of them that we detect is affected by the solar cycle. So why are energetic particles important for exoplanets? And there's kind of two different reasons. So the first one is that energetic particles can lead to the production of prebiotic molecules in exoplanetary atmospheres and on the surface of the planets. And the second reason is that they can affect sort of developed life, and that life that's already present on a planet by damaging the DNA. And so you can see here in the bottom panel that the particles impact on the exoplanet's magnetosphere, and then depending on the energy of the energetic particle, they may be able to get past the magnetic field of the planet, or otherwise they'll be deflected towards the poles. And once they go through the magnetic field of the exoplanet, they cause these particle showers in the exoplanetary atmosphere, and then the secondary particles are what actually impacts on the surface of the planet. And so that's basically where you get these prebiotic molecules formed, either in the exoplanetary atmosphere, so where they dump the first bit of their energy, or then also on the surface of the planet. And so this is why I'm interested in galactic cosmic rays and stellar energetic particles. So how can we, what do we need to know about the solar system so that we can look at it in the past? So what we know, we know lots about the solar system, which is great. And so we have detections now of the galactic cosmic rays from outside the solar system in the local ISM. And this is known from Voyager 1 and 2 measurements. So we can constrain the spectrum of galactic cosmic rays, so how many we get, how many we detect from outside the solar system. And then we can detect on Earth, which is known from instruments like Pamela. And so that can tell us how much the flux of galactic cosmic rays has changed as they've traveled through the solar system, interacting with the magnetic field of the solar wind. So we can use this to kind of calibrate our models. And then what we can do is we can change the solar wind properties. So we can like look back in time using a stellar wind model. And then that allows us to look at cosmic rays at earlier times in the solar system. So this kind of allows us to investigate what were the conditions that we think were present when life began on Earth. And then all this can also be, applied to other exoplanets as well. So I'm going to just focus on the sun. And I've talked about the galactic cosmic ray spectrum. So here I'll just show you a picture on the left, or a plot. So we look at the intensity of cosmic rays as a function of their kinetic energy. And the green dots are the Voyager data that were measured outside the solar system. And the black dashed line, the black solid line, is a fit to that data that we use. And then at Earth, we detect the blue and the cyan and magenta. This is a spectrum that we detect at Earth of galactic cosmic rays, and then the red is a model fit to the data, or from the model that I use. And so you can see that the low energy cosmic rays are really suppressed in energy. So there's about 2 to 3, 2 and a bit orders of magnitude suppression at sort of any of the energies of the cosmic rays. So they're suppressed in an energy dependent way. And that's because they interact with the solar wind in an energy dependent way. So if you're a GeV particle over here, the level of suppression is much less. And then if you're a very high energy cosmic ray, so 10 or 100 GeV, you really don't change, your energy doesn't change at all. But there's fewer of these particles, and then so they're not necessarily very important because there's not so many of them. And this is also called the modulation of galactic cosmic rays, just in case I say that word. And yeah, I think it's something to do with the magnetic field. So this suppression is known as the modulation of galactic cosmic rays. And this also depends on the magnetic solar cycle, as I mentioned. So the level of galactic cosmic rays that we detect on Earth moves up and down depending on the solar cycle. And just some of the physics about what's happening to the galactic cosmic rays. So what they do is they diffuse into the solar system. So they're bouncing off the magnetic field perturbations. So they don't travel straight in, they kind of do a little, they random walk into the solar system. And then what's leading to the suppression of their fluxes, and that is basically because the solar wind is moving outwards and it's magnetized. And so the velocity of the solar wind pushes the galactic cosmic rays out. So that's protecting us from these high energy particles. And then there's another last term for the galactic cosmic rays, and that's to do with the divergence of the velocity, so of the velocity field. And that's basically because the solar wind is expanding, and this causes a further energy loss for the cosmic rays. And actually, sorry, back to the first point where I mentioned that the galactic cosmic rays diffuse into the solar system. This is actually an energy dependent process. So the lower energy cosmic rays find it more difficult to get in. It takes them longer, so the stellar wind can eject them out in the same amount of time, whereas a higher energy particle moves more directly, can get into the solar system faster, and so the solar wind isn't as good as ejecting them out. So this is kind of linking into the stellar wind modeling. So what we really need to know about the stellar wind is the magnetic field strength and the velocity as a function of radius in the solar system, and then also looking back in time. And the last thing that we need to know to model the galactic cosmic ray propagation, or the stellar energetic particle propagation, is the astrosphere size. So the galactic cosmic rays are only experiencing this interaction in the astrosphere, within the astrosphere. And so we use the astrosphere radius as a boundary for our simulations. And this is basically calculated by a pressure balance between the interstellar wind, so the ISM ram pressure, and the stellar wind ram pressure. So we can calculate this from our model, and then look at this as we go back in time. So since we know the size of the astrosphere or the heliosphere for the sun at the moment, and we can kind of rewrite this pressure balance in terms of the current astrosphere size, and then we can use the mass loss rate as a function of time when we're looking back in time, and then the mass loss rate for the current solar wind, and this will give us the heliosphere size at younger times. And because the mass loss rate of the solar wind and the velocity of the solar wind was faster and stronger in the past, this means that the sun's astrosphere will be larger in the past. And this is basically further protection for the solar system from galactic cosmic rays. So this is just a plot. I'm sure you're all familiar with the properties of the solar wind. So this is just a plot to show you what we use in our model for the energetic particles. So we have the magnetic field of the solar wind here, with given by the blue line, and with the two components from Br and B phi, and then the velocity is given by magenta. And this is just really to actually indicate some of the ranges of the values that we look at. So the terminal wind velocity for the solar wind now is 440 kilometers per second, roughly. And at younger ages, when we go back to about 600 million years old, then the velocity of the solar wind goes up to 800 kilometers per second. Similarly, the magnetic field strength gets stronger as you go back in time, and reaches about 7 Gauss for the stellar ages that we consider. So the last thing we need to use our stellar wind model, which comes from Carlin et al. 2019 over here. So we need to know the rotation rate of the sun as a function of age, and we take this one of these scaling laws from Galactic and Bouvier 2013. And I've just highlighted here at 600 million years old, which is as far back as we considered in our model. There's a scatter here for what the rotation rate of the sun could have been at this age. So we don't know what the sun's rotation rate was at this time. And so this introduces additional scatter into our energetic particle modeling, because we don't know what the sun's rotation rate was at this time. So using the magnetic field strength, velocity, and base density of the wind, we put this into our 1.5D stellar wind model, and then we propagate our energetic particles through the stellar wind. So these are some of our results. We use the LIS, which is the local interstellar spectrum, which I showed before. This is the model fit to the Voyager data, and we keep this constant as we go back in time as well. And the black line here is this is the observations of Earth. So we look at a range of ages. So the magenta is if you look further into the sun's future, actually, and so we'll get more galactic cosmic rays reaching Earth at 6 gigayears. And then as you go back in time, this is basically when you go down the plot, and the galactic cosmic ray fluxes start to become more and more suppressed by the solar wind. And at 600 million years old, as I mentioned, we don't know whether the sun was a fast or a slow rotator. So the red shaded region shows the range of values that we might expect at this time for the galactic cosmic ray intensities. And so at kind of below GeV energies, it introduces like a factor of at least 10 difference, depending on whether the sun was a fast or a slow rotator. And the general kind of trend, which we find, which agrees with previous work, which didn't use a stellar wind model to do this, is that you get more suppression with increasing stellar rotation rate, and that's because the velocity and magnetic field strength gets stronger, which is more effective at suppressing the galactic cosmic rays. I'm just going to focus in on one of those lines from my previous plot, and this is looking at the galactic cosmic ray intensities at 1 gigayear, which is when we think life began on Earth, approximately. And the green line here shows what our model gives us, and this is the flux of galactic cosmic rays at this time. And you can see at GeV energies, it's at least an order of magnitude smaller than what we see on Earth presently, which is the gray dashed line. And so this is giving us our first kind of initial clue for what the conditions present when life began on Earth. So we know, well, it seems that it would be very likely that there were far fewer galactic cosmic rays. And you can see even at 130 AU, which is approximately the size of the sun's heliosphere at the moment, so the galactic cosmic rays have had to travel in from 950 AU, and already at 130 AU, they're more suppressed than what we see at Earth at the moment. So the stellar wind is doing a very good job of suppressing the galactic cosmic rays. But what about the stellar energetic particles? So as I said, for the sun, this sketch here shows the blue dashed line shows sort of a representative spectrum of one of these events that we would see at Earth. So this plot, I've kind of averaged something that is variable in time. So this is if you divide by basically the time interval of the event. So this wouldn't always be here. And you can see in comparison to the galactic cosmic rays, which I've shown in green, how it's just enormous in comparison to the galactic cosmic rays, but only for a very short amount of time. So that would be a few days, sorry, or a few hours, not the whole year. And then what we've done here is I've looked similarly at the stellar energetic particle spectrum when you go back in time. And what we're motivating in my paper, this recent paper here, is the blue solid line. And this is the stellar energetic particles fluxes at the surface of the star at 600 million years old. And the main things to note about this spectrum that we really motivate in this paper is that the spectral break, which is this point here, so for the sun, it's about 20 to 200 MeV, depending on the event. But we really motivate that when you look at a young star, this maximum energy or momentum the star can accelerate particles to should shift to much higher energies, so to GeV. So the sun gets more effective. As the sun has a stronger magnetic field, you have more magnetic energy, and there's more flare events. And this means that you start to push the maximum energy up to GeV energies. And the sun itself, even it also accelerates to GeV energies in large, strong flares. So we know the sun is capable of doing this. And so this is why in the past, it's more likely the spectral break occurs at GeV energies. And this line, so we also estimate how because the flares from the sun, there are more flares for younger stars, then this should become a more continuous sort of event. So unlike the solar energetic particles, which only happen for like a day or a few hours, the stellar cosmic rays for young ages should be more constant in time. And
3 minutes.
Great, thanks. So why do we care so much about the energy of the particles? And that's because it impacts on the exoplanetary atmosphere. So if you're a higher energy particle, you can penetrate further into the atmosphere and you cause different effects. And that's why it's very important to increase this, or not, to be sure about what the spectrum looks like. And so then we use, so how much energy can we put into the cosmic rays? And we take a fraction of the kinetic power in the solar wind. So we use 10%, which is similar to supernova remnant efficiencies. So this is basically the solar wind power, and 10% is the cosmic ray luminosity. And we scale this back with time. So we have more energy available at younger times in the solar system. So this is the results. So to answer the question of when do stellar cosmic rays dominate over galactic cosmic rays, so they dominate at all ages, but at 1 gigayear, it goes up to about 4 GeV in energy over the galactic cosmic rays. And we estimate here by the red dashed lines that anything below the dashed line, so the lower energies, are probably continuous in time, and anything above that is less continuous in time. And so here we're just comparing the blue shaded region is the stellar energetic particles in comparison to the galactic cosmic rays. And you can see that the spectral break starts to shift to higher energies as you go back in time, and the flux also increases. So we can say that at earlier times in the solar system, the stellar energetic particles would have been much more important than they are at the moment for the solar system. And I'll just finish with why are energetic particles, or what can we do with JWST? And as I mentioned, they have chemical effects in exoplanetary atmospheres. So these are known as fingerprint ions if they, are only really caused by cosmic rays, or they can also, as I mentioned, drive prebiotic molecules. They can also cause fake biosignatures, which is another reason why it's important to constrain the fluxes that are impacting on exoplanetary systems. And this is something that we've started to kind of move towards doing. And so these are some of the molecules identified that we should look for. And here I'm just showing for 600 million years old, one of the slices that I showed previously, we take the spectrum at 1 AU and we propagate it down through an exoplanetary atmosphere for a hot Jupiter. And then these fluxes of energetic particles can be used in the future for chemical modeling. And I've picked out this system because the exoplanet is located at 20 AU, so it'll be easier to constrain the galactic cosmic ray spectrum at this radius rather than the stellar energetic particles. Cool. So I'll just leave you with my conclusions, which are that for the galactic cosmic rays, at 1 gigayear, the GeV intensities would have been much lower than the present day values. The stellar energetic particles are much more important and they dominate over the galactic cosmic rays. And just to point out that HR2562b is probably a good candidate to observe at JWST to look at the galactic cosmic ray intensities. And thank you, and I'll take any questions.
Thank you, Donna. Very nice talk. Do we have any questions? Yes, Victor's got his hand up. Go for it, Victor.
Hi, Donna. Yeah, thanks for a great talk. I'm not sure if I missed this, but do we know anything about what the galactic cosmic ray intensity was in the past, kind of over evolutionary timescales? Because I guess that might make a difference to some of your results as well.
Yeah, so there's some evidence. I don't think from very, very far back, like
sure,
millions of years. I don't think we have a lot of constraints on that. We can tell, say, from the tree rings, if they look, you can tell when there's been like a big solar flare or something like that. And we could tell also that due to, from meteorites, that I think it's magnesium 26 or aluminium, that's a decay product of aluminium 26, that the solar system might have been close to a supernova remnant when it was young, and that would be very young, so when the disk was still present, so a T-Tauri star. But kind of in between that, it's very hard to tell, which is why it's so interesting to look at this for exoplanets, where we can detect the chemical signatures, which will constrain the energetic particle spectrum, because we don't have so much information from the past from the solar system.
Sure. Okay, thank you.
I think Louis Ahmad was next, so if you have a question.
Hi, thank you. It was a really interesting talk. Actually, just to go with Victor's question, how much do we expect the galactic cosmic rays to be different in space, like in different places in the galaxy, and where, like for different planets?
So we don't, so there are gamma ray observations where they can look at, so the gamma rays are produced by proton-proton interactions, and so that can tell you about the spectrum in different parts of the galaxy. And I think I mentioned, well, I didn't mention it, but there was a reference for Aharoni in 2020, so that they've looked at different parts of the Milky Way, and basically the galactic cosmic ray spectrum looks like it's very similar in different parts of the galaxy, which is good because it means you can use a similar spectrum for the different locations in the galaxy. But whether it changed as you go back in time is less clear, because the galactic cosmic ray spectrum is produced by mainly supernova remnants, and that comes from your star formation rate. So if the star formation rate of the Milky Way changed in the past, then that will impact your galactic cosmic ray spectrum as a function of time. But just if you're looking now for different parts of the galaxy, you're probably okay to use the same galactic cosmic ray spectrum, unless you go towards the galactic center, where there's a slight indication that there's a higher flux in the galactic center. Yeah.
Which would make sense. Thank you.
And one last question from Simon, I think.
Hi, Donna. I just quick question. You might have said this, so I might have missed it. You said that the width of the heliosphere is a function of the mass loss of the sun. Do you count for the ambient medium, sort of molecular clouds and things like that, that in the local area that the heliosphere could be passing through?
Yeah, so for my work, I don't. So it's a balance between the ram pressure of the stellar wind, as you mentioned, and then there's the ISM ram pressure. So I keep the ram pressure of the ISM constant for my simulations. I go back in time, but we do, like for individual exoplanets, as Amanda's going to talk about actually in a while, we do have ISM properties for different systems. So then for those particular systems, we're able to we know more about the ISM for those exoplanets. But for the sun in the past, I think the sun obviously has been through, different places in the galaxy. So there were higher densities at certain points if it went through a molecular cloud but I don't take that into account. There has been work done on that actually. So that would change the size of the astrosphere, which I don't include in my models. Hope that answers your question.
Yeah, thanks.
I didn't mention it, so yeah, it was a good question.
Okay, thank you once again, Donna. Nice talk. So